I'm really excited that we're having this webinar today. I just have a few quick housekeeping items to go over. As I'm sure many of you have been in on Zoom and different web calls since the beginning of 2020, I'm going to ask that everyone goes on mute for the duration of the webinar today. That'll just allow us to have really clear presentations without any background noise. So thanks for that consideration at the beginning of this webinar. I'd also like to let everyone know that we're going to be recording today's webinar. Our goal is that hopefully we'll be able to have this up on the U.S. Women in Nuclear website sometime later this week, so that if you guys are interested, you can come back to the webinar, or if you love it so much, you can pass it along to a friend and they can watch in their own time. Today, I'm really excited. We're going to have two different speakers. First, we'll be hearing from Kelsa Palomares. She is a senior nuclear engineer with Analytical Mechanics Associates. Our second speaker will be Kelly Lively, who is currently the program manager of radioisotope power systems at Idaho National Labs. So following our speakers today, we're going to have a brief Q&A session. I'll be moderating that. So you guys feel free, as you're watching the presentations, to pose any questions you may have in the group chat. You'll find that at the bottom of your screen. Feel free to post your questions there, and then we'll go through those with the speakers at the end and hopefully have a great discussion and get to learn even more. So without further ado, I'm going to go ahead and introduce our first speaker, Kelsa Palomares. She is currently serving as a senior nuclear engineer in the Advanced Projects Group of Analytical Mechanics Associates, as I mentioned earlier. She has received degrees in mechanical engineering and nuclear engineering from the Pennsylvania State University, as well as a Master of Science in Materials Science and Engineering and a PhD in nuclear engineering from the University of Tennessee. Dr. Palomares' background is in the design, testing, and experimental investigation of new and novel concepts for nuclear thermal propulsion through development programs at NASA Marshall Space Flight Center, Oak Ridge National Laboratory, and the Center for Space Nuclear Research. Recently, she has participated as the reactor subsystem lead for an industry nuclear thermal propulsion flight demonstration study commissioned by NASA and led by Analytical Mechanics Associates. Currently, she's providing subject matter expert to ongoing nuclear thermal propulsion fuel development efforts for NASA's Space Nuclear Propulsion Project. So Kelsa, we're really excited. You can feel free to go ahead and share your screen and get started whenever you're ready.
All right, thank you, Ashley. Can everyone hear me okay?
Yep, I can hear you, Kelsa.
Awesome. Okay, I should be sharing my screen now. All right, well, first and foremost, I want to start off and say I'm very excited to be speaking with you all this afternoon, and I hope you're having a great day so far. Thank you very much, Ashley, for the introduction. So as Ashley introduced me, my name is Kelsa Palomares, and I'm a nuclear space systems engineer at Analytical Mechanics Associates. For the past year, we've been supporting NASA in an industry-led study of NTP flight demonstration options, and also we've been providing them with systems engineering support throughout their NTP development efforts for the past 4 years. So today I'd like to kick off the conversation talking about powering space missions with nuclear fission power and propulsion. All right, so we just want to start off this talk with some benefits for a vision for in-space power and propulsion. I'm sure, as you're all aware, I'm speaking to a good audience, that nuclear energy has the capability to provide high power levels for long periods of time. Fission is an option to provide the potential for a high power density per unit mass. And when we get up into space, mass is really everything. So having that flexibility to provide high power densities much greater than what we can get out of conventional state-of-the-art chemical or solar power sources as we go farther and farther away from the sun is going to lead to the potential to enable more complex missions and add robustness and capability to our baseline missions. There are 3 fundamental applications of space power and propulsion. The first would be surface power, utilizing fission as a source of power to provide electricity to the crew, life, or mission support. Beyond just providing power to the crew, we can also look at leveraging this high power density as a propulsion method as we go much farther beyond where we've gone before. Two options of this would be nuclear electric propulsion and then nuclear thermal propulsion, NEP and NTP. In NEP systems, fission would still generate power and electricity, but we use that electricity to power a high efficiency thruster. For long durations, if we're able to use this thruster, we can enable fast transit to far away destinations, so much farther beyond cislunar space, destinations such as Mars. For nuclear thermal propulsion, we're using fission now as a heat source. There's no electricity power generated in this type of system. Instead, the reactor just acts as a heat exchanger, and this allows for higher efficiencies than we can get with chemical engines, but comparable thrust levels. So this allows both long and short durations, both in cislunar space or beyond. These sound like pretty far out there technologies, and our next speaker will point to some of the technologies that we developed with the RTG systems that have enabled space missions. While we haven't been able to enable successful space missions with fission power systems yet, there does exist an extensive development history of these technologies. Unfortunately, we're not yet at the technology readiness level where we've been able to put these technologies up in space and demonstrate their full capability. So I just want to take a few seconds to point to the rich history we do have in the US, even though we haven't gotten these technologies to the point that we're readily using them in space. And I know for me, if I go back and I think about the spirit of our space program, definitely the Apollo era is what's going to capture that spirit. And one of the most famous speeches during the Apollo era was JFK's moon address. And even if you're not a real space buff, you probably know this quote that comes from this address. And that was JFK capturing, "We choose to go to the moon in this decade and do other things, not because they're easy, but because they are hard." And then he goes forward and he sets forth a list of technologies that we'll need to enable exploration to the moon and then beyond the ultimate goals of where we wanted to go with the Apollo program. And we've been able to come forward and develop most of the technologies on his list. But the second one, which was the development of a nuclear rocket, he said, quote unquote, "This gives promise that someday, providing the means for even more exciting and ambitious exploration of space, perhaps beyond the moon, and perhaps to the very end of the solar system itself." So that definitely is the spirit that has made up our historic programs and we still take with us forward today. So when we think about historic space power programs, that would be generating electricity using fission and then either providing power to the crew or to power a thruster and propel ourselves in space. One of the most famous from the US side would be the Systems for Nuclear Auxiliary Power, or the SNAP program. And under this program was our only reactor that we launched into space, which unfortunately had a mechanical failure and we were not able to demonstrate its full capability. So a lot of heritage there for the space power side. There have been some other development efforts listed on this slide as well, some joint development with the USSR, and then moving forward, funding for these technologies is traditionally very cyclical, but moving forward to the 80s and 90s, trying to look at going beyond the moon again and using power for higher energy applications and going to destinations such as Mars. The other option, nuclear thermal propulsion, I have an image here of JFK visiting the nuclear rocket development station. There was extensive development put into nuclear thermal rockets as well. However, they did not get to the same readiness that we saw under SNAP program. Under the Rover program, which was the most extensive nuclear rocket development program, there were over 20 reactors ground tested, and they demonstrated the basic physics of what it would take to put one of these rockets together and actually go about and operate it. Never got into space, but we did get to the point where we were integrating these reactor systems with engines and showing how the whole system works together and it performs its function. So a lot of great strides there. And moving forward from that program, we've looked at a lot of different options for NTP now that we have that grounding in physics, that it works, and we continue to develop these programs to today. When we think about today and NASA's current needs to support their future strategic goals, fission power and propulsion technologies do support NASA's needs. So we know that we have ambitious goals that we want to go and stay on the moon and then go beyond and explore Mars. So we're going to need advanced propulsion to get to explore Mars, and then we also need sustainable power if we're going to stay on the moon. So nuclear fission technologies can support NASA's missions in this way. One thing I would love for everyone to get out of this talk is when we think about fission systems and enabling space missions, it's high power levels for long periods of time because of that great power density we can provide from the uranium and the fission source. So this is just a plot showing where that nuclear reactors compared to state-of-the-art methods, chemical, solar, or radioisotopes can really provide that high electric power levels for a long duration of time. And conversely, for nuclear thermal propulsion, high thermal power. This is really straightforward to enable fission power systems. But when we think about propulsion systems, we also need to think about the rocket science portion of the equation, and that would be specific impulse and thrust. So when we look at systems and what we develop advanced propulsion technologies, we want to consider both the specific impulse and thrust that we can provide from these systems. So first and foremost, thrust is going to be the forward force that accelerates the rocket. And essentially what we're trying to do is maximize the exit velocity we can get out of the propellant, which is basically the rocket fuel, and maximize the mass flow rate. In terms of specific impulse, this is sort of the miles per gallon we can get out of the rocket. So what we're looking for is a propellant, remember the rocket fuel, and we're trying to maximize its temperature at the exit and minimize its atomic mass. So when we look at both nuclear thermal propulsion and nuclear electric propulsion systems compared to the best chemical state-of-the-art methods, we can see nuclear thermal propulsion, we're getting twice the miles per gallon, but still at the comparable thrust levels. And then for nuclear electric propulsion, we can get an order of magnitude greater miles per gallon, but it comes at the penalty of low thrust, and that's just due to the high efficiency thruster. So ultimately, we have all the recipe ingredients we need. We're showing demonstrable benefits that we can carry more power with us per lesser unit of mass, and we're also providing higher efficiencies. And when we look at this in the whole trade space of trying to satisfy the architecture, you think of everything you need to tack on to actually go and be sustainable at Mars and perform science. We're ultimately getting to a complex trade space for the selection of the most desirable advanced propulsion system. So this is where really the trade going between chemical, NTP, NEP, other electric propulsion methods, that's when it gets really tricky. But in general, the goal for any future propulsion system is to maximize performance, the thrust and specific impulse, while minimizing mass. And fission systems can really allow us to get there, and they look like a good choice in the trade for future advanced propulsion technologies to go to Mars. So when we think about current technology development efforts in the US for these systems, I am very happy that in the past few years, the past decade pretty much, there's been significant development of these systems within both the Department of Energy and NASA. One of the big thrusts recently has been surface power development, so developing fission power reactors to provide electricity on the surface or wherever it's needed through the Kilopower project, and which is now currently transitioning out of the game-changing development program to an actual technology demonstration mission for consideration for a flight demonstration. And through these development efforts, surface power has really demonstrated many of the principal reactor technologies needed to enable near-term space mission needs. So you can see in this lower right-hand corner on the left-hand side, the kilopower project culminated in the development and testing of an actual nuclear reactor. For the propulsion side, also good strides have been made there. Most of the effort has been focused on nuclear thermal propulsion, also funded through NASA's Game-Changing Directorate, and now transitioning to a technology demonstration mission under the Space Nuclear Propulsion Project. However, unlike surface power, you have that trade NTP or NEP when you want to go and look at developing these propulsion methods. And that's really going to fall out of your mission needs. The mission really drives what are the requirements that you want out of these advanced propulsion systems. And right now we're in a phase of planning. So there have been multiple FY20 studies looking at different propulsion architecture selections for Mars. That's when NTP and NEP really shine. So we've had the Mars Transportation Assessment Study, the MTAS study led out of NASA, where they're looking at a variety of advanced propulsion technologies, including NEP and NTP, and what would be the requirements of those systems. Also, sort of falling out from that, there's been the recent NASA Engineering and Safety Center study where SMEs have evaluated what is the readiness of the different components that would make up these systems to help NASA get a clearer picture of what's the readiness level overall for these systems to support Mars missions. And then lastly, there's ongoing efforts from the National Academy of Science, Engineering, and Medicine also to evaluate NEP and NTP. So exciting time. Specific to in-space demonstrations, there have been multiple FY19 and FY20 studies on different nuclear thermal propulsion options and architectures that would make a good in-space demonstration to actually, once again, recapture and demonstrate NTP as a feasible technology and demonstrate its capability. So there have been 2 flight demonstration studies led by NASA, one which has prioritized near-term traceable high TRL solutions. So basically, what is the technology that can get us up there soonest? And then also another study which looked at near-term and enabling capability. So what is the technology we can get up there quickly, but also show enhanced capability during the flight demonstration? So basically get more bang for our buck if we wait a little bit. And then led by my company, we've also had an industry study of different NTP concepts that could be used for a flight demonstration. So what type of flight demonstration could industry support, and what would provide the most value from looking at that trade? So in summary, I'd just like to cap off with just in general, we have these new in-space challenges and new needs, and they will require new innovations if we want to fulfill our goals. Reactor technologies can enable very high energy densities for more capable propulsion and power technologies that we're going to need to go, land, live, and explore outer space. NEP and NTP, those are advanced in-space propulsion options. They provide demonstrable performance benefits compared to the state-of-the-art chemical methods. Fission surface power also provides a versatile, robust, high-power source for sustainable surface operations and exploration. And I really believe that industry has the opportunity to play a key role in the development and demonstration of future space fission power systems. Right now, I just want to point to there are current NASA demonstration missions that NASA is seeking industry support. So for fission surface power, there is a request for information out from industry, and they have a debriefing tomorrow. I included hyperlinks to the RFI in my slides. And also, space nuclear propulsion is in a pre-solicitation notice phase where that is also available at sam.gov, and I've hyperlinked it in my slides as well. Beyond NASA, also some DoD applications. So DARPA is also looking at demonstrating NTP technologies through their demonstration rocket for agile cislunar applications, or their Draco program. All right, and with that, I would like to say thank you very much for the opportunity to speak to you all today, and I'm looking forward to future questions and discussion later. Thank you.
Thank you so much. It's been great to learn a little bit about the background of these technologies and understanding the history of the programs and where the technology is headed in the future. Also, just so everyone is aware, we are going to be able to get the slides out to everyone, whether that be through email or through posting to the U.S. Women in Nuclear website later on this week. So you'll have access to those links and extra information that Kelso was kind enough to provide in her slides. So moving on to our next speaker. Our next speaker will be Kelly Lively. She is the Program Manager for the Radioisotope Power Systems at Idaho National Labs. Kelly is an engineer and is serving as the project manager for NASA's Mars 2020 mission that we've all been seeing in the news lately. Her priority at work is to enable deep space scientific exploration, and she primarily works by managing a team of engineers and technicians to fuel, test, and deliver radioisotope power systems. Today, she'll be going over some of the technology and the INL processes that are performed to enable these scientific missions, and she'll also touch on 3 space missions, the New Horizons, the Mars Science Laboratory, as well as the Mars 2020 Land Rover mission. So without further ado, Kelly, I'll hand it over to you. Oh, Kelly, it looks like you might be on mute. So if you want to turn your mute up.
Sorry about that. Thank you for inviting me to speak today, Ashley. It's my pleasure to present to you information about radioisotope power systems, and I'm just going to share my screen, hopefully. Oops. Operator error over here, bear with me. Okay, can you see my screen?
Yep, we can see.
Great. Okay. Okay, so radioisotope power systems, our programmatic mission is to fuel, test, and deliver radioisotope power systems and related technologies for use in remote, harsh environments such as space. And we do that by deploying radioisotope thermoelectric generators. And what are ETGs, or RTGs, excuse me, they're an electrical generator that converts heat generated from the radioactive decay of plutonium oxide, in this particular case, into electrical energy using thermoelectric devices. So an illustration here about those thermoelectric devices that convert the heat into electricity, they do that by a phenomena called the Seebeck effect. And it's just a thermoelectric circuit composed of materials doped in semiconductors, and they're configured in such a manner as to provide electricity from that heat from the radioactive material. Now in this illustration, it's an illustration of a multi-mission radioisotope thermoelectric generator. It's why we have acronyms. It's the MMRTG, and in the central cavity of it, you see some orange looking blocks. Those are the ones that contain the radioactive material, the plutonium oxide fuel, and that generates the heat. Now you need a temperature difference as the Seebeck coefficient prescribes in order to get this electrical circuit to work. So you get the heat generated in this particular 125 watt electric unit at about a working temperature of 900 degrees Fahrenheit. And then you use the coldness of space to provide a temperature difference. So coldness of space is really, really cold. So a big temperature difference. Not very efficient units, only about 6% in efficiency in converting heat into electricity. But it does that through those thermoelectric modules that you see down at the bottom of your screen that are blown out there. Now we have had 60 plus years of missions that have used this technology, and it illustrates all of those missions. So we have had 8 RTGs on near Earth orbit missions, primarily used for weather satellites, such as Nimbus, the Lincoln experimental satellites for communication, also 8 RTG planetary missions. There's Pioneer 11, Voyagers 1 and 2, which continue to send back information to the Earth that were launched in the 70s. Ulysses, which was a mission to investigate the polar regions of the sun. Cassini mission, which has been more recent in our history, that was launched in '97 and was a mission to Saturn. New Horizons was the first space mission that Idaho National Laboratory was involved in providing the radioisotope power system for. It was launched in January of 2006. It continues on into the Kuiper Belt, sending back information to us today. We've had 5 RTG moon missions. They were the Apollo Lunar Surface Experimental Package missions, 4 RTG Mars missions, Viking 1 and 2, the Curiosity rover, and most recently the Perseverance rover. In addition to the RTG technology, we also the Department of Energy supplies radioisotope heater units. And these are truly just little heater units. They're small plugs or small capsules of plutonium oxide fuel, still generating that heat, but not converting it into electricity. And these on the missions that are listed there were just placed around instrumentation to keep them warm. Okay, so Idaho National Laboratory certainly does not work in a vacuum on Earth anyway. The Department of Energy, Office of Nuclear Energy, engages 3 national laboratories in order to support development of the fuel, manufacturing of the fuel clads, fueling, testing, and delivery of the radioisotope power systems, and then ground operations launch support. So 3 of the 17 DOE national laboratories are involved. And this slide just depicts some of the products that are provided by each of the national laboratories. So Oak Ridge National Laboratory, a shout out to them. Certainly without any of the national laboratories, we would not be able to provide NASA with these power systems. So Oak Ridge National Laboratory provides the plutonium oxide in powder form. It is sent to Los Alamos National Laboratory to pelletize it. Oak Ridge also provides some of the cladding material for the pellets that you see there from Los Alamos National Laboratory. And then finally, these fuel clads are sent to Idaho National Laboratory in order for us to fuel private industry supplied power systems. And then once fueled, we deliver these power systems down to Kennedy Space Center for launch support. So I mentioned earlier that the first space mission that Idaho National Laboratory was involved in is New Horizons. And you see the New Horizons spacecraft in the upper left-hand corner. If you do not recognize me, I'm the cute second one from the right. And you see the nuclear power system, which is a 300-watt electric system cantilevered out from the spacecraft there. We're dressed out in clean room suits because down at Kennedy Space Center, really exciting part of the mission for us is the first time that the nuclear power system is mated to whatever it's powering. In this case, it was New Horizons, and in that picture, it would be powering all of the onboard instrumentation for that mission. Down in the lower right-hand corner is the most recent mission, and that is the Perseverance Mars rover. And you see the multi-mission radioisotope thermoelectric generator, MMRTG, there in that picture, and the ground operations crew standing behind it. So these are some vital statistics of those 2 particular systems. Again, 300-watt electric for the GPHS RTG and about 120 watts electric for the MMRTG. Certainly more radioactive material in the larger unit than in the MMRTG. So how do we get these power systems from the national laboratories to Kennedy Space Center? We work in several different facilities. In the upper right-hand corner here is just an overview of our materials and fuels complex, which is located outside of Idaho Falls, Idaho. It takes me about 45 minutes to get to my front door of my home, to my office front door, and I am coming to you today telecommuting from my home in Idaho. I am on a 14-day quarantine as a result of coming back from the launch of Mars 2020. The center picture there is a picture of our nuclear facility. There you see two buildings. The rear building would be the nuclear facility. It's a 10,000 square foot facility, which houses the capabilities that I'm just going to quickly run through next. And then we also have some laboratory spaces that we utilize to prepare some of the materials that we use in the fueling of the power systems, and that's the engineering development laboratory that you see below that. So here in this picture, I'm just going to run through the capability and some of the processes that we go through. But this picture is a close-up view, and I think really the heartbeat of what we do. You see a red glowing cylinder in the center picture, and that is an actual picture of a fuel clad before it is encapsulated in an iridium cladding, which is in the attached picture to its left. So 2,700 degrees Fahrenheit is the centerline temperature of this fuel clad before it's put in the cladding. And you see in the upper right-hand corner a bird cage. That is actually 9516 cask, and that is how those fuel clads are shipped from Los Alamos National Laboratory to Idaho National Laboratory. So inside our nuclear facility that you just saw a picture of, you would find the equipment that we utilize to fuel and test the power system. So this is the module assembly glove box, and this is where we would assemble fuel clads into the general purpose heat sources. There's an assembly drawing on the bottom left of the general purpose heat source, and each one of those 4-inch by 4-inch by 4-inch aeroshells contain 4 fuel clads. So each of those fuel clads contain about 150 grams of plutonium oxide, and it is in the form of a ceramic pellet. So really the heartbeat of what we do is to insert the fuel clads into these aeroshells and then stack those those aeroshells and insert them into the central cavity of the power system. And the center 2 pictures on the bottom are photographs of the fueling process of us putting those fuel clads into those aeroshells. Private industry certainly plays a large role in what we do because they're the ones that build and electrically test the power systems. And here you see receipt of an MMRTG from Aerojet Rocketdyne out of Pasadena, California. The red shirts, what we lovingly call our nuclear technicians, are unpackaging the MMRTG, and they're going to transport it into a mini hot cell for us to do the fueling. And that's what you see them doing here. So the center lowest picture is an MMRTG being inserted into the chamber that you see on the bottom left-hand corner. So a very small hot cell. And in this hot cell is where we would take 8 fueled modules, and you see those modules in the stacking picture in the center of this particular slide. There are 8 of them. Each of them contain, again, 4 fuel clads for a total of 32 fuel clads, if I did my math right. And on the right-hand side, you see the fuel stack being translated over to the central cavity of the power system and slowly being lowered into that power system. And certainly when we get finished up with fueling the power system, it is now operating and conducting 120 watts of electrical energy as soon as it is fueled. So it is generating electricity even as we lower that fuel stack into that cavity. There's no on and off switch to it. Once it's fueled, we are always generating the electricity. A question that is often asked is, how long do these generate electricity? The half-life of plutonium oxide fuel in it is 87 years. So these are designed for 14-year life mission plus 3 years of storage here on Earth. So even though they're only designed for a total of 17 years to operate, they will operate for decades beyond that. And Voyagers 1 and 2 are a testament to that. They are still generating electricity and communicating with Earth, launched in the late 70s, both of them, and they are now well outside and the first and are the furthest terrestrial objects in outer space. After we fuel the power system, we put it through a series of acceptance tests. And these acceptance tests are designed to simulate the environments that it will see during its mission. So there's vibration testing that simulates the launch pad environment and the Qmax environment as it goes into outer space. And then in the case of Perseverance, when it lands on Mars. This is mass properties testing, where we measure the center of gravity and the moment of inertia. Magnetics testing, where we map the electromagnetic signal that it is generating. It is generating DC power. And then lastly, thermal vacuum testing, where we simulate the near Earth space environment of a vacuum. And we can also simulate the coldness of space. And we take final power readings just to make sure that in that kind of environment, we are generating the power in which it was designed to emit. So these capabilities and testing all culminate when we transport the power system down to Kennedy Space Center for some ground operations. You see our transportation trailer there on the left. The power system itself is inserted in the 5-ton shipping cask that the Department of Energy or Department of Transportation approves. That cask is the cylindrical picture more towards the center. The facility that we're unpackaging that cask and getting to our nuclear power system is at Kennedy Space Center. And then the picture to the right is the Atlas V rocket that Perseverance will eventually be inserted into and launched. And I've got some more pictures of that coming along. Okay, so if you weren't aware, Mars 2020, there was a contest and several names were submitted with from grades K through 12 across the nation to provide to NASA for them to down select a name for the rover. And you can see some of the names that were chosen there, or that were down selected to, and then Perseverance was the final name. You see a picture of Perseverance rover attached to the descent stage in the clean room facility at Kennedy Space Center in the top left. And then if you're not aware, there are 10 million people throughout the world whose names were etched into 3 microchips that went along with this rover. You also see the booster, the United Launch Alliance booster that was being offloaded from the aircraft. So certainly INL does not claim to be even a big partner in the making of this successful mission, but it's great to be a small part of history. Okay, so the Perseverance rover, these are pictures from the hot fit check. So again, this is where we would attach the nuclear power system to the rover for the first time. And I would draw your attention to the picture in the center. The rover is placed upside down in the spacecraft. So that's why it's upside down here. And this gives opportunity not only for to make sure that the rover systems are going to work with the nuclear power system, but also gives yet another opportunity to practice mating it. Okay, and then the fairing encapsulation goes on in that same building. The building is at, as I said, at Kennedy Space Center. It's in the upper left-hand corner there, and you're seeing photographs from within inside. So you see the rover encapsulated in the spacecraft on the bottom left, and then it being encapsulated into the fairing on the right. Okay, and then finally, the power system is taken over to Cape Canaveral Air Force Station, where it will be hoisted from the ground level up to the mezzanine near the top of the fairing. So it's about a 200-foot lift on the outside of the building, and that is at the launch site where the power system is mated to the rover, which is inside the spacecraft, which is inside the fairing, which is on top of fueled rocket, about launch minus 9 days. Okay, and then finally, we get to see that fantastic launch. It's exciting every single time. I give a little map there of some of the launch sites at Cape Canaveral Air Force Station, and then a picture of the launch. And then a selfie down at the bottom of the Mars Science Laboratory Curiosity. So that is a selfie taken on Mars, and it is a collage of several pictures that were taken to make the image that you see there. And there's also some pictures of yet to be successful. You've got to land that rover on Mars. If you get the opportunity, you should go Google the 7 minutes of terror, and it shows an illustration of the landings, entry, landing, and descent of the rover onto the Martian surface. So the Mars 2020 mission is slated to arrive on Mars on February 18th of 2021. Its primary mission will be to collect soil samples in the stainless steel tubes that are on her undercarriage. And she will collect and cache those samples for a future sample return project. While I'm on the topic of missions, New Horizons, as I said, is still out there sending data back to us. It was successful in its 9.5 year journey to Pluto to send back this first picture. And wouldn't it be NASA's fortune for Pluto to have a heart shape on it in that photograph? You see that picture there. It will certainly always be near and dear to my heart, as this was my first mission. And I was an individual contributor to testing, delivery, and ground operations during that mission, but it went on to investigate a Kuiper Belt object named Ultima Thule on New Year's Day in 2019, and it continues on into the Kuiper Belt to continue exploring. The Mars Science Laboratory Curiosity, its mission has also been extended a couple of times, and this is the one we fuel tested and launched while we were waiting for Pluto New Horizons to get to its destination. It continues to stroll along, collecting soil samples and sending information back. Future missions, we are looking forward to the exploration of Saturn's moon Titan with Dragonfly. This will be a 8 rotorcraft. It will be powered by an MMRTG, the movement of it as well as the instrumentation, as is the rover Perseverance and also Curiosity. So we're looking forward to that launch in 2004. As our previous speaker had indicated, we are also involved in nuclear power fission systems. So these are larger wattage systems used for surface power and nuclear thermal propulsion or nuclear electric propulsion. As she stated, I won't spend a lot of time on that. Just know that these are larger power systems, and INL does have a hand in those collaborations as well. And lastly, and I'll stop talking so you can actually ask some questions, you can follow us on all of these social media sites. And as Ashley had indicated, I think she's intending to post these slides, so you'll get to look at them if you're interested in a little more detail. And again, thank you so much for having me. It's been my pleasure to talk to you, and I look forward to answering any questions that you may have for me.
Thank you so much, Kelly. This has been really fascinating. I really enjoy getting to see kind of the story of the Perseverance rover and getting to hear more about the other programs and missions that are ongoing right now. So it looks like we have about 3 different questions. So I know that most of you guys out there do have questions. Feel free to put them in the chat and I will go through them as well. Our first question is actually for Kelsa. This participant, Patricia, was asking how exactly a nuclear powered propulsion system would get into space. She suspects that we cannot launch a rocket into space from the Earth using nuclear power. So what would be the mechanism to get it into space?
Oh yeah, so if we use the rocket with the nuclear reactor to go into space, that would be like a single staged orbit. And yes, you're correct, we typically don't do that. So we would just launch it like we launch any traditional in-space propulsion system where you have the similar booster engines, and you just build your launch vehicle and you put it up into space. There has been some recent changes to what are the considerations with launch and operating nuclear reactors in space that have been released by the White House in the past 2 years. So that's another thing that you can check out, is what are the real restrictions and how does a fission reactor differ than a radioisotope system, and what's need considered to actually get it up off the ground.
Great, thank you so much. Our next question, I believe, is geared toward Kelly. This person's asking, where are we getting the plutonium-238 these days? Also, where is the neptunium coming from? This person thought most of what we had in the US was processing material from former US weapons program or potentially from Russia, but she suspects that those sources are gone now. So she was curious to where we're getting those materials. Oh, Kelly, sorry, I think you're on mute again.
It's like my thing today. Sorry about that. So yeah, you're exactly right. So INL actually stores the nation's supply of neptunium that is used to make targets. Oak Ridge National Laboratory, we ship that neptunium oxide in powder form to Oak Ridge National Laboratory. They insert it into targets. They make pellets out of it. It's quite a process. But they make pellets out of the neptunium, insert it in long cylindrical targets, and those are inserted in one of 2 reactors, HIFER at Oak Ridge National Laboratory and the Advanced Test Reactor at INL. Bombarded with neutrons in those reactors and then sent back to Oak Ridge National Laboratory, where it is made into plutonium oxide powder. And then that powder is shipped to Los Alamos and feeds the supply chain for them to make the pellets sent to us for fueling power systems. So that's how it works. Previously, we have bought plutonium oxide powder from Russia. Yes, that is true. We still have a supply of that as well. So that material cannot be used in any kind of weapons programs. It has to be used for peaceful missions in space programs. So that is what it is utilized for. And that supply is stored at Los Alamos National Laboratory awaiting processing there. So we have started making small amounts of plutonium oxide in the United States again, and we are gearing up. It's the Department of Energy's goal to make 1.5 kilograms of material on an annual basis. So that's the goal we're working towards, and there is some US made from Oak Ridge National Laboratory plutonium oxide fuel on Perseverance.
Wow, that's really awesome to hear about. There was a similar guided question is if we are running out of neptunium. I think you might have touched on that a bit, but just to, I guess, to reiterate.
Yeah, we have a lot of neptunium oxide, so no fear of running out of that.
Okay, great. And another question came in going back to launching using nuclear fission. I guess the participant is curious if it's a private launch, if it's not, I guess if it's not government organized, do we need to comply with an EPA?
And what would PA mean?
Sorry, the abbreviation is NEPA. I believe it's the...
Oh, no.
Okay.
I am not by any means an expert on what it would look like for commercial launch, but I am going to assume the government will form some sort of regulatory committee, which you would have to abide by government regulations. I'm thinking that probably the government efforts will be the real pathfinder, and then they will set up regulation following that commercial industry can look towards. But it's not set in stone, so I think there's a lot of opportunity there as well, since it isn't set in stone.
And so I would add along those lines, the National Environmental Protection Agency, we follow under those guidelines for nuclear launches for those NEPA actions to take place. So that is notifying the public of what the dose consequences are to the public should there be an accident. During that whole process, there is information communicated to the public in the areas where those launches would take place that would be within the band of area that could be affected by some kind of accident. So, and I'm speaking from RPS mission, or radioisotope power systems missions. I certainly do not have any expertise in the nuclear reactor realm and space exploration, but NEPA actions are performed by the federal government and were performed for the Perseverance mission, the Mars 2020 missions, and all of the previous nuclear launch missions.
Great, thank you so much. I think that will definitely answer the question, or at least provide some background information for everyone. We did get in another question. Would it be possible to refuel the reactor for longer voyages, or would the craft be limited to the lifetime and output of one fuel cycle? If so, what might storage and resupply entail for a nuclear-powered spacecraft?
So I would say traditional programs, we've really looked at the reactor to be possibly disposable after completing the mission. However, some of the more advanced concepts have looked at reactors that would be refuelable, both for fission surface power missions or propulsion applications. In those type of reactors, you're going to be really limited by the geometry of your fuel that you're using to actually enable that refuel. And then for the fuel cycle, since we haven't had a sustainable and we haven't had a demonstration yet of these systems in space, I think that's really open territory. But there's been a lot of concepts put out there that you could refuel your reactor, or you just design a reactor that's capable of very high burn up.
Great, thank you so much. Kelly, did you have anything to add? It's okay if not.
No.
Okay. Okay, thank you so much. And it looks like we've got just two more. When we talk about the fission systems that you talked about, Kelsa, what is what's the biggest challenge that you faced in running these demonstrations and trying to progress the technologies further?
The biggest challenge typically is for any system almost is the materials. So coming up with the materials that can have a sustainable and reliable lifetime within the reactor, and making sure that the system is safe to operate because we made the right selection of materials and component design. So going into any demonstration, you want to set yourself up for success. And because we're pushing to such extreme applications in both systems using exotic working fluids and either really, really high burn up or really, really high temperature, it's really new territory for materials development. And there's many other hurdles, but materials is usually the first one that you'll want to get over that we haven't gotten completely to where we want to be, especially for NTP systems.
Okay, great. Thank you so much. And I guess if anyone else has any more questions, feel free to send them in, but I'll read our last one. This is to Kelly. It's more about just the experience of getting to be present for the launch. You know, this person was asking, what exactly was it like to be around for the launch? What was the most exciting part? They imagine it would have such a cool atmosphere to be a part of. And can you elaborate on that experience?
Yes, unmuted. Look, originally, finally. Yeah, the launch truly is the apex of the entire mission. These missions for INL are about 5 years in duration. So we take care of the fuel and the power system and are working on that project, around 50 of us for a long period of time. We haven't had the opportunity to fuel and test a spare unit, so it's very important for us to be able to do this correctly and without error the very first time. So we put a lot of pride in the work that we do to get it to the Cape. So I've had the opportunity now to be in different positions for 3 different space missions, each of them exciting in their own way. Being an individual contributor on New Horizons, project manager on MSL, and now a department manager and also a project manager, looking forward to my retirement and getting to see people fill the roles that I was once in has been absolutely delightful to witness and be a part of. Rolling the rocket out onto the launch pad really is one of the moments that I really look forward to and appreciate. And with every single one, I've been able to witness that from about maybe a half a mile away. And so can really see the whole thing and get to share that with coworkers. And every single mission, it's brought tears to my eyes, just to be that little part of history. And a girl that grew up in the cornfields of Illinois, went to a small engineering college in Idaho, and now gets to support NASA missions. Who would have thought? I certainly didn't when I was growing up in those cornfields in Illinois. And then spectacularly, just the energy of the rocket leaving the Earth certainly brings chills and much applause and more hugging from team members as we've been able to witness it go into space. We will also get the opportunity, we'll have a landing party here in Idaho and get to see streaming from the Jet Propulsion Laboratory to see their control room and their reactions. And so we'll have that party, and we look forward to it in February to get together again and be able to see that, because I can't imagine being those engineers who have to wait all of that time to see if their systems are going to work, you know, having gone all those millions of miles and then through the entry, launch, and descent stage. Quite spectacular on their end as well.
Yeah, I can only imagine. That must be such an amazing and special experience and such a great team to be a part of. So thank you so much for sharing some of those details as well. I really appreciate it. It looks like we're just about out of time. I just really wanted to say another big thank you to both of our speakers. I'm so appreciative of both of you taking the time to talk with everyone today. It's been wonderful to have a DC Women in Nuclear event this year. I know some of our events earlier this spring were canceled for safety precautions due to everything that's going on with the town just due to the coronavirus. So it was wonderful to put together an event, and I hope all of our participants felt equally inspired and got to learn something new and fascinating today over their lunch break. So with that, I just want to say thank you again to everyone, and I'll conclude this webinar. Bye.